Welcome to homework.
In this problem, we have two smooth disks which are moving toward each other as shown. They then collide and move apart. We want to determine their speeds after impact. We choose our y and x axes as follows. So the y-axis is along the line of impact. Now, we can write our velocities, our known velocities as follows. So VA y1, where subscript 1 denotes before the impact, is equal to 15 times 3 over 5. And so along the y-axis, this is 9 meters per second in that direction. Now along the x-axis, VA x1 is equal to 15 multiplied by 4 over 5, and this is 12 meters per second to the northwest. So we have our x and y components of the initial velocity of A. For B, we do the same. So VB x1 before the collision is 8 meters per second purely along the x-axis. And that's not the x component, that is the y component. The x component, VB x1, is equal to 0. So we see B moves purely along the y-axis, so the x component of its velocity initially is 0. Now that we have the velocities, let's apply the coefficient of restitution. So we know the coefficient of restitution, taking the right direction along our y-axis to be positive. The coefficient of restitution E is equal to VB y2 minus the AY2 over VA y1 minus VB y1. And we know this coefficient of restitution, as it is given in the problem, to be 0.8. So this is equal to VBY2 after the collision minus the AY2, these are both unknown, over minus 9 minus 8. So we get an equation here. VA y2 minus VBY2 is equal to 13.6. So we have an equation here with two unknowns. We'll call this equation 1. So we'll need to set up another set of equations, and we can do this by using the conservation of momentum in the y direction. So the conservation of y momentum. So we'll take this direction to be positive, and we'll apply the conservation of momentum. So before the collision, the momentum ma va y1 plus the momentum of b mb vb y1 must equal to the momenta after the collision. ma va y2 plus mb vby2. And so let's substitute what we know into this equation. The mass of A is 4 kg times its velocity in the y direction minus 9, plus B's momentum is 2 times its velocity 8. After the collision, the momentum of A is 4 times VA y2 plus 2, the mass of B, into vby2. So now we have, if we simplify, we have 2, so we divide both sides by 2, vay2 plus vby2 is equal to minus 10. And we'll call this equation number 2. So if we solve our two equations, since they are the two same unknowns, we solve 1 and 2 simultaneously, we find vay2 is equal to 1.2 meters per second to the northeast, and vby2 is equal to minus 12.4 meters per second, which is 12.4 meters per second in that direction. So those are the y components. We can now find the x components by again using the conservation of momentum, but now in the x direction. So essentially the conservation of x momentum. Now, since no impact occurs along the x-axis, the component of velocity of each disk remains constant before and after the impact. So very simply, VAX2 is the same as before the collision, VAX1, and this is 12 meters per second in that direction. Now, VBX2 is equal to VBX1, and this is equal to 0. So B has no component of velocity along the x-axis before or after the collision. So now we can calculate the magnitude of the velocities of disks A and B just after the impact, which is what we require. So VA2 is equal to the square root of the sum of the squares of the x and y components. So that's the square root of 12 squared plus 1.2 squared. And so we get VA2 after the collision. A moves off with speed 12.1 meters per second. After the collision, disk B has velocity VB2, which is the square root of 0 squared, its x component, plus its y component, 12.4 squared. And so the speed of B after the collision is 12.4 meters per second.